If you have been watching my videos for a while or know me personally, you already know one thing about me. That is, I always take calculated approach, not in real life, but definitely in mechanical design. Calculated design, calculated selections, calculated tolerance. This channel tagline, design is a calculated art, and I truly mean it. But when it comes to bolt or a screw sizing, 90% of time I do not actually do any detailed calculations. Instead, I rely on experience or some simple thumb rules. And if you're a design engineer, you are probably doing the same. And trust me, there is nothing wrong with that approach. You don't need to calculate every bolt size. For example, let's say you are designing a mounting bracket for a pneumatic cylinder. So first off, cylinders already comes with a standard threaded holes for its mounting. So you can simply use the bolt size as specified by the cylinder manufacturer. No calculations needed. Similarly, to mount the bracket, something like this, you can use the same bolt size or go one size up because the load over the bolt is more or less same. No calculations is needed. It's just common sense, right? Now, on other side, there are some situations where we must do the calculations, especially where safety is concerned. For example, in hydraulic systems, the mounting bolts for heavy hydraulic presses. Where loads are in tons, we cannot rely on experience or instinct sizing. Another example could be bolted joint in a high torque and high speed drivelines, where the bolts are subjected to dynamic loading, not just simple tensile static loading. Another critical situation is when the joints is subjected to continuous vibration or impact loading. In such cases, bolt sizing becomes crucial. And as a design engineer, this is our responsibility to not only calculate the bolt size, but also select the right grade of bolt and specify the optimum preload for the bolts to prevent the failures. And this is exactly what we are going to learn in this video. This is Ayush from Master Mechanical Design, and this video is a complete guide to the bolt sizing in machine design, covering both the calculation method for critical situation and simple thumb rule methods for non-critical situation. First, we will master the calculation method with practical industrial examples. In one example, where the bolts are in simple static tensile loading, and in one example where the bolts are in shear with dynamic loading. And after that, we will understand the bolt grades, their standards, and how to choose the right grade according to the application. And as I mentioned earlier, in most of case, 90% of case, where situations are not critical, then we can rely on simple thumb rules and experience. So I will also share 4 simple thumb rules for bolt sizing. So my main aim is by the end of this video, you will exactly know when to calculate bolt sizing and how to do it, and when we should avoid the calculation method and confidently rely on simple thumb rules to save the time. So make sure you watch this video till the end. Now, before we going into the bolt sizing calculations, we need to understand the strength of a bolting connection doesn't solely rely on the size of bolts. Even if the bolt size is adequate, but if it's not tightened with proper preload, it can get loose or fail under vibration due to fatigue failure. Also, if the thread depth is not enough, the bolt can be failed due to lack of thread locking long before it's failed due to lack of strength if bolt is undersized. And there are also some misconceptions, like people believing that putting a washer increase the bolt strength, but it's not. So, before moving to the bolt sizing calculations, let's first address the basic. Let's revisit the fundamental concept of bolt, nut, and screw. And believe me, even if you have a great experience, there are some things that we completely missed out from starting. So, what is a bolting connection? So, bolting is a completely non destructive fastening method, which means using the bolting connection, we can assemble and disassemble the two or multiple parts as many times as needed without any destruction. Unlike welding or riveting fastening, which is one time fix, and this can be only disassembled by destroying the part. Now, the bolting connection can be done in two ways. One is with a nut, the bolt and nut method, and another is without a nut, the screwing method. In the bolt and nut method, we make through clearance holes in two or more components and insert the bolt from one side and then tighten the nut on other side using a spanner. We may also need to hold the bolt head with another spanner or a Allen key. And in a screwing method, we make an internal thread in one component, either through or blind, and then insert the bolt directly into the threaded component, tightening it by turning the bolt head. The interesting thing to note is that bolts used with the nut are technically called bolts, while the bolts used without a nut directly into threaded component are called a screw. They are essentially the same component but having different name based on how they assembled. Now, the choice between bolting and screwing depends on application. The bolting method required a free space around the nut, which can be a problem when we put one part over another. Also, we need to rotate the nut while holding the bolt head, which can be inconvenient, especially in compact machines. So, to overcome this problem, the screwing method is more convenient in such cases, as you only need to tighten the screw without having a nut. However, a screwing method is not suitable for the components with a thin cross section, like sheet metal, where threads may not form properly. As per the thumb rule, for a steel bolt, in a steel tapped hole or in a nut, the recommended thread engagement is minimum 1 time of the bolt diameter. Whereas for a steel bolt in a soft material like aluminum, brass, or cast iron, the thread engagement should be at least 1.5 to 2 times of the bolt diameter. And for the steel bolt in very soft material like plastic or wood, the thread engagement should be at least 2 to 3 times of the bolt diameter. In reality, not all the engaged thread carrying the same load. The first few 3 to 5 threads near the loaded face, the bolt head or nut face, take most of the load. This happens because thread deforms slightly under load, and the first engaged thread is the stiffest, carrying the largest share of the load. If the thread engagement is too short, the threads will strip before the bolt reaches its tensile capacity. But if the engaged thread is too longer than needed, it doesn't add any additional strength. It just wastes material and increases manufacturing cost. Now, it's also important to consider cost factor. Making the clearance hole is generally more economical than making threaded holes. So, in heavy structure where you need lots of fastening, we prefer bolting method. We avoid threaded holes. This video is sponsored by Zeekal, a CNC manufacturing service for consistent quality parts every time. In mechanical design, the real pain is finding the different manufacturers for different types of part, and then deals with inconsistent quality and slow turnarounds. And Zeekal fix this with simple flow. You just upload your CAD file like a STEP or XT, and Zeekal provides quotes from trusted shops in US and worldwide. You can also quick chat with machinist and get a quick DFM check and stay updated while part is being manufactured. And then every part is inspected before shipping and you get the tracking. The unique thing about Zeekal is the nameplate archive, a digital recipe of your part design, tolerances, and how the part was made. So when you need to reorder the same part, you just scan the QR code and place the order. You will get the exact same part with same result from same manufacturers and same machinist. Sometimes you need part faster, right? So Zeekal also provide madness mode, same day machining and overnight shipping. So value is clear: consistency, speed, and one point of contact. And yes, the quality is backed by AS9100 and ISO 9001 certification, which means they maintain aerospace level manufacturing quality. And if you order with my promo code AYUS2025, you will get 10% of discount on your order. The link is in description. So let's back to our topic. Now let's understand how a bolt or a screw connection actually works. So when we tighten a bolt or a screw, after some turns, the bottom face of the bolt head or the nut face touches the component. If we will stop here and do not tighten any further, the bolt will not really lock. It can be easily loosened. And if we pull the joints in an axial direction, even with a small load, a small force, the parts will be instantly separate. Why? Because the load goes directly to the bolts, stretch it slightly. For a normal application, this might be acceptable. But in case of flange with a gasket seal, even a small stretch in bolting can cause leakage. Also, if the shear load is applied, the part will slide until they directly contact the bolt. And this puts bearing stress on the bolts, which can cause sudden failure. So to properly lock the joints, we apply preload to the bolts or the screw. That means after bolt head touches the component, we continue tightening by a certain angle by a certain torque. This stretches the bolt slightly, putting it in tension, and at the same time it's compressing the jointed parts. And as a result, everything locked together because of friction. And we can actually calculate the locking frictional force. Friction equal to mu into N. Mu is the coefficient of friction. For mild steel, dry surface usually 0.2 to 0.5. Let's take 0.3 for calculation. And N is the normal force, which is in this case the preload force. So how much preload we should apply? So as per the thumb rule, the preload should be set to about 70% of the bolt material yield strength. So the preload force can be calculated as 0.7 into yield strength into tensile stress area. Let's understand it with an example. Let's assume the bolt size is M10 and grade is 8.8. We will talk about bolt grades later in this video. So the yield strength of the grade 8.8 is 640 MPa. And the weakest cross section is at the threaded section, because threads reduce the diameter. So the weakest cross section area can be calculated as D minus 0.382 into P. where D is the bolt diameter and P is the pitch. So put the values, it will be 8.6 mm. But this is the diameter of the bolt. We need to calculate area. So area equal to pi d square divided by 4. It will be 58 mm square. So put the values and it will be around 26 kilonewton of preload. Now to apply this preload, we use torque wrench. So we need to convert this preload into tightening torque. And the formula is tightening torque equal to preload force into bolt diameter into nut factor. Nut factor depends on several conditions, typically consider 0.2. So it will become 52 Newton meter. And if we check the torque table, the recommended torque for M10 bolt grade 8.8 is around 57 Newton meter, which matches our calculation. But there is a problem. The torque method isn't very accurate. A lot of applied torque is lost in friction in threads and under the bolt head. In fact, the accuracy is only plus minus 25%. This is why in critical applications like aerospace, the preload is directly measured by checking the bolt elongation using vernier clipper or ultrasonic devices. However, for general applications for factory machines, torque wrenches are still widely used. So in our case, applying 52 Newton meter torque produces a preload of about 26 kilonewton, which is roughly equal to 2.6 ton of force. This stretches the bolt and compresses the joint with the same amount of force. And because of this, something very interesting happens. That is, when an external tensile load is applied, it doesn't go directly to the bolt. First, it reduces the clamping force between the parts, and only some amount of force transferred to the bolt or screw. The total load doesn't transfer to the bolt. The total amount of load does transfer to bolts only after preload is overcome. And this has a big benefit. Under vibration or impact loading, only the part of load transferred to the bolt. The bolt doesn't experience full cyclic stress, so the bolt doesn't go under fatigue failure. So in short, the preload is not only properly locking the joints, but it's also increase the life of bolting connection under vibration in impact loads. We can also see the benefits in shear loading. So with the preload of 26 kilonewton and coefficient of friction 0.3, frictional resistance will be about 800 kilogram force. This means the joint can resist approximately 800 kilogram force of shear load before any relative sliding occurs between the parts. Up to this limit, the external shear is full balanced by the frictional resistance generated from clamping force. In other words, if the shear load is less than 800 kilogram force, it doesn't transfer to the bolts. It is absorbed entirely in contact surface of the joints. So we can say the preload doesn't increase the strength of bolt itself, but it's improved the reliability of the bolting joints. It's preventing losing, reducing fatigue, and avoid direct shear or bending stress on bolt. So never ever compromise on bolt preloading. Now, what about washer? Do they increase the strength of bolting connection? So in short, no. A washer doesn't increase the load carrying capacity of bolt itself. The bolt still takes all the tensile and shear load to its weakest cross section. So no matter how thick or what type of washer we use, the maximum capacity of bolt only depends on the weakest section, cross section, and the bolt material, or we say the bolt grade. So why do we use the washer? So the first purpose is to distribute the load. A bolt head or nut has relatively a small bearing area, and a washer increases its contact area, reducing the surface pressure on the joints. This is extremely useful when joints materials are soft like aluminum or brass, where the bolt head otherwise shrink into the surface during tightening. So by spreading the load, the washer helps to maintain the clamping force. Second purpose of washer is to protect the surface. During tightening and retightening, the bolt head or nut rotate against the joint surface, which can cause wear or galling. But with a washer in place, the washer takes the wear instead of the joint material. Third is it's improve the frictional locking. If the joint surface is rough or uneven, a washer provides a smoother and large contact area. This increases the friction at interference, which helps to prevent the losing of the bolt or nut under vibration. Also, if there's a slot, washer is extremely useful. So washer do not makes the joint stronger in terms of tensile or shear capacity. Instead, it's make the joints more reliable and durable by distributing the load, protecting surface, and improve frictional resistance. And now let's finally understand the bolt sizing calculation, means how to estimate the bolt diameter for a given amount of load. So first let's assume the bolting connection is well established. Means the bolting is tightened with a proper preload and having a washer, and also thread depth is well enough. So in this case, the bolt joint can be only failed if bolt itself breaks. And when the bolt will break? Well, a bolt will break when the applied load exceeds its ultimate tensile strength. After this point, the bolt material undergoes necking and eventually fractures. However, in most of bolt sizing calculations, we do not consider ultimate tensile strength as a design limit. Instead, we use yield strength. And here's why. Once a bolt reaches yield, it's permanently stretched. And this permanent stretch causes the loss of preload. Means the joint loosen even if bolt hasn't fractured yet. So during design, we ensure the stress in bolts doesn't exceed its yield strength under the applied load. And the amount of stress in a bolt depends on what? The applied load and the cross-section area of the bolt. So to sizing the bolt means to find the diameter of the bolt, we just need to calculate the cross-section area of the bolt, A. So let's rearrange the formula. So the required bolting area A equal to force divided by stress. And for stress, we will consider yield strength of the bolt material. Now, the loading can be tensile as well as shear. So depending on the type of loading, for tensile loading, axial loading, we use tensile yield strength. For shear loading, we use shear yield strength, which is usually about 0.58 times of tensile yield strength of the steel. And here we also need to consider factor of safety. So this gives us the total required cross-section area of the bolt. Let's call it X mm square. Now we need to understand a typical bolting connection contains two or more number of bolts. So we have two options. One is select the number of bolt first. Let's say if we decide to use n number of bolts, then the each bolt area must be X divided by n. Total required cross-section area of the bolt divided by total number of bolt. And then we can calculate the each bolt diameter using pi d square divided by 4 and calculate for d, diameter of each bolt. But if the bolt size is limited due to plate thickness or a space constraint, then we can select the bolt size first. And then we can calculate the cross-section area of the bolt we chosen. And let's call them bolt area A. Then we can calculate the number of bolts required, x divided by A. Simple enough, right? But if you're feeling a bit confused, don't worry, let's go through the numerical example. Let's imagine we have a wheel loader. You know what wheel loader do? Construction, right? Now, suppose I want to attach a hook to the back side of the wheel loader to pull something really heavy, let's say up to 20 tons. So the question is, what bolt size should we use to safely make these bolting connections? So first step is convert the load unit. 1 ton equal to 1000 kg. So 20 tons means 20,000 kg. Multiply by gravity 9.81. 196200 Newton force. Now before calculation, first step is select the right grade of the bolt. So let's first understand what the bolt grade is. So a bolt grade is nothing but classification of its strength defined by international standards, and different standards use different numbering system or symbols. ISO metric standard, the most widely used, use the numbers like 8.8, 10.9. Then Shear standard, inch bolt standards, use grades like 1, 2, 5, 8. Higher the number means higher the strength. You can also identify them from the head marking, something like this. Then another American ASTM grade, they are like A307, A325, also linked with Shear standard. Then JIS, Japanese standard, very similar to the ISO standard. In this video, we will only talk about ISO metric grades because they are most common in machinery and automation industry worldwide. So according to ISO 8981, bolts are classified into 10 specific grades. Each grade is written as a two set of numbers separated by the points. Now, these numbers are not random. They directly represents the tensile strength and yield strength of the bolt. For example, grade 10.9, take the first set of number 10 and multiply by 100, 1000 MPa. That's the minimum tensile strength of this grade of bolts. Then multiply the first and second number and then 10 times 900 MPa. That's the minimum yield strength of this grade of bolt. You can check the same with the table. And that's the beauty of ISO standard. Everything is well engineered and structured, unlike some national standards. Now, you can check the data for the bolts. So when we check the strength of the bolts, you will find three important parameters. One is proof stress, the maximum stress a bolt can take without permanent stretching. Think of this as a safer limit of the preloading, usually 90 to 95% of the yield strength. Second is yield strength, the stress at which bolts start permanent deformation. And this is what we use for the bolt design. And third is tensile strength, the ultimate limit, the maximum stress before breaking. And we do not design on this limit because once the bolt or any material reach its yield limit, it means it's already failed their function. So in short, for the bolting connection, proof strength is for checking the preload limit, yield strength for design calculation, and tensile strength for knowing the absolute capacity. Now let's understand how to choose the bolt grades. So the grades below 8.8, they all are low carbon steel, not heat treated, low strength, used in light application like covers, panels, or plastic part. It's just cheaper in manufacturing and cost. Now, grade 8.8 are medium carbon steel, quenched and tempered, having balanced strength and toughness. So, this is the most commonly used grade in a machinery or automation. Even in SPM design, I used to default to 8.8. Then the grade 10.9 or 11.9, they are alloy steel, high strength, and used in high load and high vibration application. For example, 10.9 used in automotive suspension, engine head blocks, crankshafts bolt. 12.9 used in aerospace fixer, precision tool, and in very high strength compact joints. Lastly, we also use stainless steel bolts, commonly in SPM and pharma industry. They have two different grades. One is A270 304 type. It's about 700 MPa yield strength. And second is A480 316 type. It's about 800 MPa yield strength. I hope you well understand the bolt grade classification. So in our case, since this is simple machinery application, mostly static but impact loading sometimes, so we can select the bolt grade 8.8. Grade 8.8 have minimum yield strength 640 MPa and minimum tensile strength 800 MPa. For the bolt sizing, we will consider minimum yield strength 640 MPa. MPa is Newton per mm square. Now, the next important step is to choose the correct factor of safety for the bolt sizing. And it depends on application. For a simple static joints, factor of safety should be 1.25 to 2 times. In common machineries with variable loads, 2 to 3 times. In cyclic or fatigue sensitive joints, 3 to 6 times depending on vibration and severity. And for the safety critical parts, factor of safety should be 4 to 8 times or use the standard codes. In our case, the load is static but sometimes impacts, so let's consider factor of safety 3. Now the next step is calculate the required bolting area. And this will become 919.68 mm square. This is the required bolting area, cross-section area to take the 20 ton of load under its yield limit. Now, we are not going to use a single bolting. Instead, we will use 4 number of bolts to mount the hook bracket at each corners. So each bolt area will be total required bolting area divided by 4, 229.9 mm square. Now the cross-section area of the bolts is circular. So area equal to pi d square divided by 4. Rearranging for the diameter, and diameter will be 17.1 mm. Now this should be the root diameter, minor diameter of the threads. So actual diameter will be bigger than that. That means we can go for M18, but for safer side, let's choose M20. So finally, to safely pull a 20-ton load, we should mount the hook using 4 number of M20 bolts, M20 screw. Now, does the thread pitch affects the strength of bolt? So yes, because it changes the root diameter. For example, M20 cross thread pitch 2.5 mm, root diameter will be roughly around 17.5, whereas M20 fine thread pitch 1.5 mm, root diameter will be about 18.5. So the fine thread bolts have larger root diameter and therefore a slight higher loading capacity. But we do not select the fine thread just to increase the strength of bolt. The main purpose of fine threaded bolts is better adjustment. especially in application like sensor. This is why you see the threads like M8 into 1 or M12 into 1 in sensors. Now let's take an example of dynamic loading condition where bolts are in shear stress. So let's suppose we have to design a Cardan shaft. If you don't know, a Cardan shaft is like a shaft and having universal joints at the both ends. It's used to transfer the torque between two shafts which are not collinear. The main advantage is it can handle the large radial misalignments. And with the spline connection, it can also adjust the axial misalignment. So let's say our Cardan shaft has a flange mountings at the end, and we have to size the bolt for this flange. And the given torque to be transmitted is 0.8 kilonewton meter, and the maximum speed is 10,000 rpm. Now you might ask, what is the role of the speed here? So we will see very shortly, and this is very interesting. Now, if you think this situation closely, the shaft and the flanges are in torsional, in twisting stress, but the bolts are in shear stress. And we can calculate the shear force by converting the amount of torque into tangential force. So we have the torque 0.8 kilonewton meter means 800 newton meter, and the radius. Now, as per the flange design and their size, the optimum pitch circle diameter PCD of the bolting to be 124 mm. PCD 124 divided by 2, 62 mm, 0.062 mm. And we all know the torque equal to force into radius. So the force equal to torque divided by radius, 12903 Newton. So this is a static shear force acting on the bolts. But that's not all, because the shaft has significant mass, and when it's rotated at 10,000 rpm and suddenly a brake is applied either on a driving or driven end, what will happen? First, the rotating flange will stop, and then it will try to stop the entire shaft. But since the shaft is already in a high speed, it will resist stopping. Why? Because of moment of inertia, and this can feel like a jerk. And this jerking force depends on moment of inertia of the rotating body and how quickly we change its speed, how quickly we stop it, or how quickly we start it. That is the angular acceleration. And the inertial torque is equal to moment of inertia multiplied by angular acceleration. Now, since this is a cylindrical shaft rotating around primary axis, the moment of inertia can be calculated using the formula 1 by 2 mr square. But because the design is complex, it's better to estimate moment of inertia using the CAD software, SolidWorks. Here, the principal moment of inertia around the x-axis, the rotational axis, comes around 0.03308 kg meter square. Now, what about angular acceleration? So, suppose we don't have directly, but instead we know the acceleration and deceleration time. In this case, let's say it takes 0.5 seconds. Means when we apply the brake, the rotation will stop just in a split of second. So, angular acceleration is equal to angular velocity divided by time. Angular velocity is 10,000 rpm. So first convert it into radian per second. So omega is equal to 2 pi n divided by 60. Put the values 1046.7 radian per second. And the angular acceleration will become 2093 radian per second square. So the inertial torque will become 69.2 Newton meter. Now convert this torque into force. So force equal to torque divided by radius, 1117 Newton. So the total maximum shear force on the bolt will be static plus dynamic. 14,020 Newton. Now the next step is select the bolt grade. We will select 8.8 grade. The yield strength will be 640 MPa, but this is tensile yield strength. In our case, the bolts are in shear, so the bolt shear strength will be approximate to 0.58 into tensile yield strength. So 371 MPa, minimum shear yield strength. Now the required bolting area will be force divided by shear stress into factor of safety. Since this is a critical rotating joint, so let's consider factor of safety 5. So the required area will become 188.8 mm square. So this is the total bolt shear area required. Now in this flange, the space is limited. We can only use M8 or M10 bolts. So let's start with M8 bolts. For M8 into 1.25, the minor diameter, the root diameter will be around 6.82 mm. So the bolt area will be 36.6 mm square. Now the number of bolts required, so total area divided by single bolt area, 15.16. So we need to select at least 6 bolt of M8 size. And of course, plain washers should be used for proper load distribution. And since this is a shear joint and also safety is critical, so the correct bolt preloading is essential. For M8 bolts, the recommended tightening torque is about 25 Newton meter. And this can be calculated as well, as we have seen earlier, but usually preload tables are used. So for this garden shaft flange, to safely transmit 0.8 kN meter at 10,000 RPM, we need 6 number of M8 bolts with proper preloading and washers. Now, as I said in beginning, that 90% of time we do not do any calculations. We rely on simple thumb rules. So let's understand 4 thumb rules that I personally use in machine design. So first thumb rule is when bolted connections are under no load or just compression load. For example, in this assembly, the servo press is simply rested over the base plate. There is no actually load on the bolts. They are just locating the press on the plate. So in such cases, you don't need any calculations. Just pick a bolt size that looks proportionate to the machine. Another example is mounting a base plate on a frame or a structure. Since the load is only compressive, again no calculations are required. You can select simply M6 or M8 bolts. Now let's say we have the 10 mm of base plate, and let's say if I want to use the contour bolt, then after the contour bolt, there should be at least 1 or 2 mm thick wall left. This means the maximum bolt size I can use is M8. But honestly, M6 would be even better. In special purpose machines, when we're free to choose a bolt size, we always choose M6 bolt size. And if something is really heavy, then M8 or M10. And for lighter application like sensor mountings, M4 or M5 is enough. Now, the second thumb rule comes from plate thickness. As per the thumb rule, in steel plates, the thread engagement length should be at least 1 time of the bolt diameter. For example, if the bolt size is 6 mm, then the plate thickness should be at least 6 mm. Otherwise, before the bolt breaks, the thread will strip. But if the plate is made of aluminum, then the thread engagement should be at least 1.5 to 2 times of the bolt diameter. So for 10 mm thick aluminum plate, the maximum recommended bolt size would be M5 or M6. Using M8 would be not optimum. Now the third thumb rule is roughly load estimation. And here is something that might surprise you. A single M6 bolt of grade 8.8 can safely take around 1 ton of tensile load. and a single M10 bolt can safely take around 3 tons of tensile load. So if your application is subjected to just 100-200 kg of force, you don't need to do any calculations. You can just select M6 or M8 bolt size. Now, the fourth thumb rule is for sheet metal. If the sheet thickness is less than 2 mm, avoid threading. Just use weld nut or just through hole with a bolt and nut. And bolt size can be M3, M4, M5. It doesn't really matter if you are using a bolt with the nut. If the sheet metal is 3 mm, then you can make the threaded connection and use the M3 bolt just to ensure there is at least 3-4 thread engagements. So this was all about the simple thumb rules for the bolt sizing, and I hope this will give you the more confidence to select the proper bolt size without always doing the calculations. Also keep in mind, the bolt sizing calculation is not for finding the smallest size of bolt just to save the cost. Bolts are not expensive. The real purpose of the bolt sizing is to prevent the failure in a critical situation or in heavy loading. So if there is no significant load, just pick a bolt size which fits in a space and look good. And this is it for this video. I hope you liked the video. If you did, please give us a like or hype the video. And thank you so much for watching this video.